Welcome everybody to the chapter, what are we on? Sorry about that, chapter 10 lecture video, and we're going to dive right in. So chapter 10 is about two main things. The first main thing, the first probably video that we'll make is all about intermolecular forces. And the second video will be primarily concerned with dealing with gas laws. Gas laws have a lot of calculations, and I hope your algebra is feeling strong. So let's get into intermolecular forces. Okay, and what intermolecular forces is all about is the interactions between individual molecules. So far, we've been spending a lot of time talking about interactions inside molecules. In other words, the bonds between individual atoms. Well, now we're going to start looking at things on a broader scope. Okay, so this particular slide is showing three different states of matter. In this case, we're sort of looking at water in particular. So we've got, on the left here, we've got a solid. In the middle, we've got a liquid. And on the right, we have gas, right? So this is sort of showing boiling water, and in particular, we're looking at the vapor up here for the gas. Now, the solid, I'm going to zoom in here a little bit on this section so I can write some things. So the solid has the least amount of kinetic energy. Okay, the least amount of kinetic energy. And that's because with the solid, all of the molecules are locked in place. They are connected to each other through various intermolecular forces, and they can't move around. Now, they can vibrate about their point of origin, but they can't slide past each other. They can't move around at all. So because of that, solids have a rigid shape and defined volume. Okay, so thinking about what we're doing going from a solid to a liquid, in this case, solid water to liquid water. In order to do that, we have to add some thermal energy. We have to warm it up, right? So we're going to put some energy into that solid, and we're going to cause those molecules to vibrate a little bit faster and a little bit faster and a little bit faster until those forces that are holding them in place are broken. Okay? And when we do that, now we have molecules that can move past each other. So we have a liquid. So the liquid has more kinetic energy because now the molecules are able to move around. Remember, kinetic energy is related to movement, right? So liquids have more kinetic energy, and because the molecules are allowed to slide past each other, we have an indefinite volume, okay, which means that it takes the shape of its container, and we all sort of know that. Like, you put some water in a glass and it takes the shape of your glass. But the molecules still have to interact with each other. They can't, there's no space between the molecules. So because of that, oh, I wrote indefinite volume, didn't I? I got that backwards. Sorry. This is just like real lecture, isn't it? This should be indefinite shape. My bad. You heard me talking about shapes, and I wrote the word volume. My apologies. But, so back to the idea of volume. But because the molecules are still in contact with each other, it still has a defined volume. Okay? So, moving along, so going from liquid to gas now we are, in order to boil water, we have to keep adding more heat to it, adding more energy. And as we're doing that, we're causing the molecules to keep vibrating faster and faster and faster and faster until finally molecules can break away entirely. The forces that are holding them together as a liquid are finally overcome, and the molecules can fly off all on their own, totally willy-nilly in any direction, however they want to go. So the gas has the most kinetic energy, okay, has an indefinite shape, and an indefinite volume. Because now the molecules are not forced to touch each other anymore. They can fly off and do whatever they want. Now, because of that, gases will fill their container. Whatever the container happens to be, they'll fill it. So it still takes the shape of the container, just like liquids do. But the size of the container will dictate how much volume you have, okay? So as we go through this, I want to remind you, when we get to a question, I encourage you to pause this video, try out the question, and then press play again, and you can follow me along. So what state of matter adopts the same shape and volume as its container? Now, solids have a definite shape and a definite volume. Okay, so it's not dictated by the container at all. Liquids have a malleable shape. It can take the shape of its container, but it has a definite volume because all the molecules are still touching. Gases, the molecules are not touching anymore, so it will assume the shape and volume of its container. Plasma is a fourth state of matter that we're not going to talk about, so we're just going to do this. And aqueous, we also haven't talked about yet. That's coming up in a couple of chapters, actually the next chapter. So we're just going to skip that. So of the three choices we have left, gas is the one that will adopt the shape and volume of its container. And that's important. Shape and volume. All right. So which of the following is true? Now I have to explain the first one. Okay. So when we go from a solid to a liquid, that's called melting. Okay. And hopefully you understand that already. If you don't, I'm not sure what planet you've been on. When we go from a liquid to a gas, that's called vaporizing. Okay, making a vapor. Now there is a third option. Going from solid straight to gas has a name, and it is sublimation. Okay, which means to sublime, right? So an example of that is dry ice. Dry ice is solid carbon dioxide. Okay, and it's most common to see the dry ice around Halloween time. But what it does is solid dry ice, it's frozen carbon dioxide. And it takes it, in order to make it frozen, you have to cool it down very, 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 very far below normal ambient temperatures that we live in. So when you take dry ice and you bring it out to room temperature, it skips right over that melting stage and goes straight from a solid to the gas. Okay? So that's what it means to sublime something. So which of the following is or are true? A, solids sublime into liquids. No, that's actually called melting. Okay. A molecule in a liquid state has more kinetic energy than the same molecule in a gas state, because liquids are more dense than gases. But if we come back up here to the top, liquids have more kinetic energy than solids, but gases have more than the liquids. Okay. So we can count this one out, and we can count this one out. Boiling water is an endothermic process. So think about what that means. We start with a liquid water, and in order to boil it, we have to heat it up, right? So we have to put heat energy into the water in order to boil it. So when energy goes in, it's endothermic. So that one is correct. particles in the gas state cannot be changed directly into solids. Well, it may not be obvious, but any of these things, the melting, the vaporizing, the sublimation, those can all go both ways, right? A liquid can freeze and become a solid, a gas can condense and become a liquid, and a gas can, we call it deposition, and become a solid. So that is also a an incorrect answer. Because gases can be converted directly into solids if you have the right conditions. So boiling water is an endothermic process is the correct answer. So now, looking at different types of matter, okay, so different ways that things can bond. So ionic, we've already sort of experienced dealing with ionic in our class, and those are things that are a metal and a non-metal, right? Calcium carbonate, right? These are all ionic solids, okay? And when we talk about ionic bonding, we are talking about two or more metal plus non-metal. Okay? And they're coming together because we have positives and negatives and they're attracted to each other, and that's how they come together. Now let's come over here to metallic. So in this example, this is only copper. Okay? There's only one thing there. So in metallic bonding, we have only one metal. Okay? So if you're trying to decide if something has metallic bonding, it has to be a single thing, only one metal thing there. Okay? So let's come down here to the molecular covalent, right? And remember, molecular is when we bond only nonmetals, right? So things like H2O or carbon dioxide. Okay? So only nonmetals count for molecular, right? And molecular covalent is the bonding of two or more nonmetals. Okay? And then the final version, network covalent. Only carbon here. That word says carbon. I apologize for my handwriting. But much like the metallic version of bonding, when all you have is a single nonmetal, you get network covalent. Okay? So diamonds, if you weren't already aware, are made of pure carbon, right? Arranged in a very particular way to make them super strong and beautiful.